once we have computed the potential resolvers for a given flaw in our plan, we need to select one of these and apply it to the current partial plan. So we refine our current partial plan using the resolver we've just computed. And the way this is done is very simple. We have to add elements to the plan, namely those elements that are specified in our resolver. So this could be an ordering constraint, it could be one or more binding constraints on our variables, it could be a new causal link, or it could be a new action, or a combination of any of those, whatever our resolver specified. In general, we have to make sure that our constraints that are maintained in the plan are consistent, but this is not required here. This is the case because our function that computes the resolvers for a given flaw already took care of that. So we never consider resolvers that would make our variable binding or ordering constraints inconsistent. But when we resolve a flaw and when we introduce new causal links or new actions, what we can do is we can introduce new flaws into the plan by doing so. And that means we simply have to update the flaws that we know about in our plan. And these are unachieved preconditions. And we've seen that earlier how this can be done with open goal computation. Or the threats. And again, we had a function earlier that does that incrementally. During our plan space search, we maintain a set of ordering constraints. And here are a few words on the implementation of ordering constraints. In fact, you could see the ordering constraints as an independent module that can be plugged into our planner and that has two access operations that we need to support. The first one is we need to query whether an action in our plan must come before another action. So we need to be able to find out whether two actions are already ordered with respect to each other. And then, of course, at some stage, we want to add new orderings to our constraint network. So we want to assert that an action AI must come before an action AJ. And let us assume that we don't have to do consistency checking when we add an ordering constraint to our constraint network. The first internal representation is this one here, where we maintain the sets of predecessors and successors for each action simply as they were given to the constraint network. So if we have an action and we say this is ordered with respect to some other action, and then we add more orderings as we go along, then we would just store these as we were given these. So I'm now asserting a third, fourth ordering here that says this action has to come before this action. So the first option is to store the orderings as given, which would store 4 ordering constraints in this case. This means we have a polynomial number of orderings that we need to store, polynomial in the number of nodes. And every time we query this constraint network, we have to compute the transitive closure. For example, if we want to query whether this node comes before this node, we have to compute that transitive closure. The second option would be to store only direct predecessor-successor relations. So in this case, we would not store this relation here. This would not be part of our internal representation. That would save some storage, but the problem is if we query the order between these two nodes, again we have to compute the transitive closure. The final option would be to maintain the transitive closure explicitly. So in this case, every time we assert a new ordering, we have to compute the transitive closure with respect to all other actions in our plan and maintain every link explicitly. That means when we query, we're very fast. But the problem is now that the assertion, the adding of an ordering, becomes a relatively slow operation. In general, there's a trade-off between space and time complexity between these different representations. But in the planner, we can assume that the query is probably the most common operation. So we want this to be the fastest, and therefore the third representation is most likely to be the best. Similar to the ordering constraints, we can think of the variable binding constraints as a module that we can plug into the planner. And then we have several types of constraints that we've already looked at. Firstly, there are unary constraints that say that a variable x has to be of a given domain. This domain is a set of values, including the case where it can be just one single value, so we have a specific value for our variable. Then we have equality constraints that assert that two variables must have the same value. So we don't know what value they will take, but we know that eventually in our final plan they must have the same value. And finally, we have inequalities where we say that two variables must have different values. The unary constraints and the equality constraints, they are quite easy. So these can be dealt with in linear time and don't cause any problems. This, however, the inequality causes us a lot of trouble because inequality constraints cause exponential complexity in this type of constraint network. So with the inequalities, this becomes a general constraint satisfaction problem, and a general constraint satisfaction problem is NP complete. In some sense, this is really bad news. Introducing variable inequalities was one of the ways we had to resolve flaws, namely flaws that are threats. So we have to deal with variable inequalities. But that means that every step in our plan refinement gives rise to an NP-complete problem that we need to solve, namely to maintaining the consistency of the variable binding constraints. Finally, our generic plan space search planner has the same two properties that our state space planner also had, namely it is sound and complete. And that means whenever our planner is given pi0, our initial plan, and that can be refined into a solution plan, then our function PSP of pi0 will return a solution plan. Or more explicitly, soundness means that if the planner returns a result, then this is indeed a solution plan, and completeness means if there is a solution plan, then our planner will be able to find this solution plan. The proof of this type of proposition is similar to what we've seen earlier. So we do it by induction, and as our loop invariant, we use that the ordering and variable binding constraints are consistent at every stage of the algorithm. So we maintain this as part of the main loop in the algorithm. Then we know that the planner only returns a plan if this plan is flawless. So the plan is flawless and the orderings and variable bindings are consistent, therefore it must be a solution plan. And completeness can also be shown by induction, this time induction on the number of actions in our solution plan. So we start off with our initial plan that contains two actions, the two dummy actions, and then we show that for every plan that is one action bigger, there exists an execution trace of our non-deterministic algorithm that can find that solution plan.